Hello friends, welcome back. In this SWAYAM course on differential calculus, we had discussions on functions, their limits, continuity and differentiability. Functions considered so far were real valued functions defined over subsets of real numbers. In this session, we extend this to real valued functions defined over subsets of Cartesian product of real numbers. We discuss domain, range and graph of functions of more than one variable in this session. Limits, continuity and differentiability of functions of more than one variable will be discussed in the coming sessions. Functions of more than one variable occurs in real life. For example, to model varying temperature in a large region, one can use a function which takes on two variables, longitude and latitude, maybe even altitude as a third, and output one variable, the temperature. Suppose we consider the temperature T that depends only on two variables, longitude and latitude, which are denoted by L1 and L2 respectively. Then T is a function of two variables L1 and L2, which we denote by T is equal to f of L1 L2. F is some complicated function that determines which temperature each longitude latitude pair corresponds with. Formally, let us begin with the definition of real valued function where the domain is a set of n tuples. That is, the domain is a subset of the Cartesian product R cross etc. cross R n times, which is equal to the set of all n tuples x1, x2 etc. xn, such that xi belongs to R where I from 1 to n. Suppose D is a subset of the set of all n tuples of real numbers n tuples x1, x2 etc. xn, that is D subset of R cross etc. cross R n times. A real valued function f on D is a rule such that to each element n tuple x1, x2 etc. xn in D, there corresponds a real number w that satisfies the equation w is equal to f of x1, x2 etc. xn. We say that f is a real valued function of n variables x1, x2 etc. xn. This set D is the function's domain. The set of w values taken on by f is the function's range or image and is denoted by range of f or image of f. That is, range of f is equal to image of f is equal to the set of all f of x1, x2 etc. xn such that the n tuple x1, x2 etc. xn belongs to D. The symbol w is the dependent variable of f and f is said to be a function of the n independent variables x1, x2 etc. xn. We also call the variables x1, x2 etc. xn the function's input variables and call w the function's output variable. Instead of the variables x1, x2 etc. xn, variables such as x, y, z etc. or a, b, c etc. may be used if they are appropriate to the situation. For a given n tuple x1 etc. xn, we call f of x1 etc. xn function's value at the point x1 etc. xn. For example, the value of f of x, y, z, which is equal to square root of x square minus y cube plus 3z at the point triplet 4, 0, negative 4 is f of 4, 0, negative 4, which is equal to square root of 4 square minus 0 cube plus 3 times negative 4, which is equal to square root of 16 minus 0 minus 12 which is equal to square root of 4 which is equal to 2. We now discuss the natural domain of a function. From the beginning session of this SWAYAM course on differential calculus, we know that if a function is defined by a formula y is equal to f of x and the domain is not stated explicitly, then the domain is assumed to be the largest set of x values for which the formula gives y values. This is the function's so called natural domain or simply domain. Thus, the natural domain of a function given by an equation is the largest set consisting of all points where the definition of that function makes sense or valid. Now, we use this idea in the case of a function of n variables. Suppose a function is defined by a formula w is equal to f of x1, x2, etc., xn and the domain is not stated explicitly. Then the domain is assumed to be the largest set of n tuples x1, x2, etc., xn values for which the formula gives w values. This is the function's so called natural domain. Hence, if the domain of a function is not defined explicitly, then its domain is obtained by excluding inputs that lead to complex numbers or division by 0. This is illustrated in the following examples. Z is equal to positive square root of 7 x raised to 4 plus 5 y square is a function of two independent variables x and y. Hence, it is a function of two variables and hence its natural domain is a subset of the plane R square. Since square root of a negative number is imaginary, it follows that the function is defined only for those ordered pairs ordered pair x y for which 7 x raised to 4 plus 5 y square greater than or equal to 0. Due to the presence of x raised to 4 and y square, we have 7 x raised to 4 plus 5 y square is always non-negative for any choice of ordered pair x y. Hence, the natural domain is D is equal to the set of all ordered pairs x y where x and y belongs to the set of real numbers. That is, D is equal to R cross R which is equal to R square. As another example, consider the function z is equal to square root of 1 minus x square minus y square. We note that z is a real number only when 1 minus x square minus y square greater than or equal to 0. That is when x square plus y square less than or equal to 1. So, D is the set of all ordered pairs ordered pair x y in the plane such that x square plus y square less than or equal to 1. That is, D is equal to the set of all ordered pairs ordered pair x y belongs to R2 such that x square plus y square less than or equal to 1. That is, D is the set of points in the disk with center at the origin and radius 1. As another example, consider the function z is equal to 1 upon x cube minus y cube. Since x cube minus y cube is equal to x minus y times x square plus x y plus y square, it follows that z is equal to 1 upon x cube minus y cube can be defined at all points ordered where x y in R2 where x not equal to y. Hence, the natural domain of the function is D which is the set of all ordered pairs x y belongs to R2 such that x not equal to y. That is, the natural domain is the set of all points in the plane that do not lie on the line x is equal to y. The natural domain partitions the plane into two by the line x is equal to y. We know that the natural domain of the real valued exponential function f of u is equal to e to the power u of a real variable u is the set of all real numbers. With this in mind, we note that the natural domain of the real valued function g of u is equal to e to the power negative u is also the set of all real numbers. With this information, let us discuss the natural domain of the function of two variables h of x y is equal to e to the power negative x square minus y square. We note that e to the power minus x square minus y square is equal to e to the power minus x square plus y square. We have x square plus y square is always a real number for any choice of ordered pair x y. Hence, for any choice of ordered pair x y, the function h of x y is equal to e to the power minus x square minus y square gives a value. Hence, the natural domain D of the function h is the set of all points in the plane, that is D is equal to r square, the plane itself. As another example, we consider the function z is equal to f of x y, which is equal to log x plus log y. The function can be written as z is equal to log x y. As the real valued logarithmic function of a real variable is defined only for positive real numbers, log x y is defined for those ordered pairs x y for which x y greater than 0. Hence, domain of z is the set of all points in the plane with the product x y strictly greater than 0. That is, D is the set of all ordered pairs x y in R square such that the product x y greater than 0. That is, the domain is the set of all points in the first and third quadrants excluding the boundary by x and y axis. As another example, we sketch the natural domain of the function f of x y is equal to natural logarithm of x square minus y. We know that the domain of the natural logarithm function is the set of positive real numbers. Hence, the function f of ordered pair x y is equal to ln of x square minus y is defined only when x square minus y strictly greater than 0 or x square strictly greater than y or y less than x square. We first sketch the parabola y is equal to x square as a dashed curve. To identify the domain, we choose the point ordered pair x y is equal to ordered pair 0 negative 1 and note that negative 1 is equal to y strictly less than 0 is equal to x square. Hence, the region is the one that contains the point ordered pair 0 negative 1 and with boundary y is equal to x square. The region y less than x square consists of all points below the curve y is equal to x square and is the natural domain of the given function. As another example, the natural domain of the function f of x y is equal to square root of y minus x square is the shaded region in the figure including the boundary by parabola. We now list the natural domain and range of some functions of two variables in the following table. Graph of a function. We know from the beginning of the course on differential calculus that the graph of a function f from the set D into the set B is defined by graph of f is equal to the set of all ordered pairs A f of A where A belongs to D. In particular, if D is the set of n tuples of real numbers and B is a subset of the set of real numbers, we obtain graph of f is the set of all n plus 1 tuples x1, x2, etc. xn, comma f of x1, etc. xn such that n tuples x1, etc. xn belongs to D. This shows that the members of the graph of f is a set of n plus 1 tuples. Hence, graph of f is a subset of the n plus 1 dimensional space R raised to n plus 1. To get a clear idea of these concepts, we first discuss this situation in the case of functions of two variables. geometrical representation of a function of two variables. Consider z is equal to f of x y, a function of two variables. Then the domain of f denoted by D is a subset of the plane. To each point ordered by x y in the domain D, there corresponds a value of z given by z is equal to f of x y. Now, we consider a triplet x y z where z is equal to f of x y. From the Cartesian geometry of three-dimensional space, we know that a triplet x y z of real numbers corresponds to a point in a space. Hence, by the definition of graph of a function, it follows that points in the graph are points in space. Hence, the graph of f is a subset of the space. From the figure, we can see that to each point ordered where x y of the domain of the function f, that is to the point ordered where x y in the domain which is a subset of the x y plane, there corresponds a point P in space with the coordinates triplet x y z where z is equal to f of x y. The locus of points P whose coordinates satisfy the equation z is equal to f of x y determines a surface in space. For example, a portion of the graph of the function z is equal to x square plus y square is the surface shown in the figure. It is a circular paraboloid or paraboloid of revolution. The cross sections of the surface by planes perpendicular to the z axis are circles centered on the z axis. The cross sections by planes containing the z axis are congruent parabolas with a common focus at the point triplet 0, 0, 1 by 4. In general, we note that graph of a function f of two variables is a surface in the space. With this observation, the graph of f of x y is called the surface z is equal to f of x y. We note that f of x y is equal to 2 is a constant function of two variables x and y. Its natural domain is obviously the entire plane. Let us graph the function f of x y is equal to 2. By the definition, the graph of the function f of x y is equal to 2 is graph of f is equal to the set of all triplet x y f of x y such that x y belongs to R 2, which is the set of all triplets x y 2 such that ordered where x y belongs to R 2, that is the set of all points in the space with its z coordinate value 2. It is the plane at a distance 2 units up from the x y plane. As another example, let us examine that the graph of the function z is equal to f of x y is equal to square root of 16 minus x square minus y square is the hemisphere above the x y plane. Since square root function gives a real number only when the domain is the set of non-negative real numbers, square root of 16 minus x square minus y square gives a real number when 16 minus x square minus y square greater than or equal to 0. Hence, the natural domain D of the given function f is the set of all ordered pairs x y such that x square plus y square less than or equal to 16. That is, the domain D is the set of all points in the x y plane which lie or within the circle whose center is at the origin and radius 4. Now, the range of f is the set of all z such that z is equal to square root of 16 minus x square minus y square such that ordered where x y belongs to D. Being positive square root, the possible values of z are always positive real numbers, so that z greater than or equal to 0. Also, z is equal to square root of 16 minus x square minus y square is less than or equal to square root of 16, which is equal to 4. Hence, the range of f is the set of all z such that 0 less than or equal to z less than or equal to 4, which is the closed interval 0, 4. By the definition, the graph of the function f of x y is equal to square root of 16 minus x square minus y square is graph of f is equal to the set of all triplets x, y square root of 16 minus x square minus y square such that ordered where x y belongs to R 2, where x square plus y square less than or equal to 16. To draw the graph of f, squaring both sides of the equation z is equal to square root of 16 minus x square minus y square, we get z square is equal to 16 minus x square minus y square, which may be written as x square plus y square plus z square is equal to 16, which is the equation of the sphere with the center at the origin and radius 4. But since z greater than or equal to 0, the graph of f is just the top half of this sphere. That is, the graph of f is a hemisphere above the xy plane. The graph of the function z is equal to f of x y, which is equal to negative 1 by 3 times square root of 49 minus 2 x square minus 3 y square is a hemisphere below the xy plane. The graph of the function z is equal to f of x y, which is equal to y square minus x square in the x y z space is a hyperbolic paraboloid or which is a saddle surface. The graph of the function f of x y is equal to 1 minus x minus y is a plane. A triangular portion of plane can be sketched by plotting the points of intersections of the plane with the coordinate axis. Here they are triplets 1 0 0, triplet 0 1 0 and triplet 0 0 1, and joining them with the line segments. Level curves of functions of two variables. While plotting places or region in a map, three-dimensional view of the place or region are transferred to a plane of map using some methods. If we go through a physical map of a country, we see that the mountains are shaded according to height, with the tallest mountain range in grey and the oceans colored according to depth, with the deepest ocean in blue and so on. At the same time, a topographic or contour map shows a three-dimensional landscape such as mountain range by means of two-dimensional contour lines or curves of constant elevation. Figure shows contour map of an island. To get a clear idea, consider the model hill and its contour map shown in the figure. Measurements are made in hundreds of feet. The contour map is constructed by passing planes of constant elevation through the hill, projecting the resulting contours onto a flat surface and labeling the contours with their elevations. For instance, if we cut the hill by passing a plane of height 700 feet, showing 7 on the side of the hill, and projecting the resulting contours onto the plane, we get the contour labeled 7 for 700 feet. Contour maps are useful for studying functions of two variables also. If the surface z is equal to f of x y is cut by the horizontal plane z is equal to k, then at all points triplet x y z on the intersection we have z is equal to k, so that f of x y is equal to k. The projection of this intersection onto the x y plane is called the level curve of height k or the level curve with constant k. A set of level curves for z is equal to f of x y is called a contour plot or contour map of f. As an example, the level curves of the function f of x y is equal to y square minus x square have equations of the form y square minus x square is equal to k. For k strictly greater than 0, these curves are hyperbolas opening along the lines parallel to the y axis. Level curves for 3 values k is equal to 2, k is equal to 3 and k is equal to 5 are shown in the figure. For k less than 0, they are hyperbolas opening along lines parallel to the x axis. Graph of f of x y is equal to y square minus x square and level curves for 3 values k is equal to negative 2, k is equal to negative 3 and k is equal to negative 5 are shown in the figure. For k is equal to 0, the level curve consists of the intersecting lines y plus x is equal to 0 and y minus x is equal to 0. They are shown by black lines in the figure. As another example, we sketch the contour plot of the function f of x y is equal to 50 minus x square minus y square using level curves of heights k is equal to 0, 25, 38 and 50. We plot the level curves f of x y is equal to 0, f of x y is equal to 25, f of x y is equal to 38 and f of x y is equal to 50 in the domain of f in the plane. The domain of f is the entire xy plane. Since f of x y is equal to 50 minus x square minus y square, which is equal to 50 minus x square plus y square, and since x square plus y square greater than or equal to 0, the range of f is the set of real numbers less than or equal to 50. The graph of the given function in xyz space is the paraboloid z is equal to 50 minus x square minus y square, a portion of which is shown in the figure. The level curve f of x y is equal to 0 is the set of points in the xy plane at which f of x y is equal to 50 minus x square minus y square is equal to 0 or x square plus y square is equal to 50, which is the circle of radius square root of 50 is equal to 5 times square root of 2 centered at the origin. Similarly, the level curves f of x y is equal to 25 and f of x y is equal to 38 are the circles f of x y is equal to 50 minus x square minus y square is equal to 25 or x square plus y square is equal to 25 and f of x y is equal to 50 minus x square minus y square is equal to 38 or x square plus y square is equal to 12. The level curve f of x y is equal to 50 consists of the origin alone, contour line. So far, we discussed level curves that helps us to picture the height at various positions of a hill in a 2-dimensional plane or paper. Mathematically, plotting level curves means we are picturing the values of a function f of x y of 2 variables in the domain of the function, which is a subset of a plane. Instead of picturing the values of a function in a plane or paper, the other way is to plot the values of the function on the surface corresponding to the graph of the function. This plotting on the surface gives a curve or line called contour line. The curve in space in which the plane z is equal to k cuts the surface z is equal to f of x y is made up of the points that represent the function values f of x y is equal to k. It is called the contour line f of x y is equal to k. We remark that the same equation f of x y is equal to k represents a level curve and also a contour line. Treating the equation f of x y is equal to k as level curve means f of x y is equal to k is a projection of the intersection of the surface z is equal to f of x y and the plane z is equal to k onto the xy plane, while the contour line f of x y is equal to k is a curve in space. Figure shows the contour line f of x y is equal to 38 on the surface z is equal to 50 minus x square minus y square defined by the function f of x y is equal to 50 minus x square minus y square. The contour line lies directly above the circle x square plus y square is equal to 12, which is the level curve f of x y is equal to 38 in the functions domain. Domain and range of functions of 3 variables. All the discussions for functions of 2 variables can be naturally extended to functions of 3 variables. With this in mind, we consider some examples where the domain and range of given functions of 3 variables are discussed. As 5x square plus y raised to 6 plus 3 z raised to 4 greater than or equal to 0 for all triplets x, y, z, the domain of the function f of x, y, z is equal to square root of 5x square plus y raised to 6 plus 3 z raised to 4 is the entire space R3. As square root of 5x square plus y raised to 6 plus 3 z raised to 4 is greater than or equal to 0 for all triplets x, y, z, it follows that the range is closed interval 0 infinity. As 1 upon x, y, z is defined only when x, y, z is different from 0, the domain of the function f of x, y, z is equal to 1 upon x, y, z is the set of all triplets x, y, z belongs to R3 such that x, y, z is different from 0. That is, the domain is the portion obtained by removing the 3 Cartesian planes from the space. Level surfaces of functions of 3 variables. The natural extension of level curves to functions of 3 variables is not a curve, but a surface called level surface. The definition follows. The set of points triplets x, y, z in space where a function of 3 independent variables has a constant value f of x, y, z is equal to k is called a level surface of f. As an example, we describe the level surfaces of the function f of x, y, z is equal to square root of x square plus y square plus z square of 3 variables. We note that square root of x square plus y square plus z square is the distance from the origin to the point x, y, z. Hence, the value of the function f is the distance from the origin to the point triplet x, y, z. Each level surface square root of x square plus y square plus z square is equal to k, where k greater than 0 is a sphere of radius k centered at the origin. Figure shows 3 of these spheres. The outer sphere corresponds to the level surface square root of x square plus y square plus z square is equal to 3. The middle sphere corresponds to the level surface square root of x square plus y square plus z square is equal to 2, and the inner sphere corresponds to the level surface square root of x square plus y square plus z square is equal to 1. The level surface square root of x square plus y square plus z square is equal to 0 consists of the origin alone. For k less than 0, there is no level surface. As another example, consider the function f of x, y, z is equal to x square plus y square plus z square. The level surfaces have equations of the form x square plus y square plus z square is equal to k. For k greater than 0, the graph of this equation is a sphere of radius square root of k centered at the origin. For k is equal to 0, the graph is the single point triplet 0, 0, 0, and for k less than 0, there is no level surface. Before concluding, we discuss the level surfaces of f of x, y, z is equal to z square minus x square minus y square. The level surfaces have equations of the form z square minus x square minus y square is equal to k. If k is equal to 0, this equation represents the cone z square minus x square minus y square is equal to 0 or z square equal to x square plus y square. If k greater than 0, level curves of f of x, y, z is equal to z square minus x square minus y square are hyperboloids of two sheets. As an example, when k is equal to 5, the hyperboloid of two sheets is z square minus x square minus y square is equal to 5 and is shown in the figure. If k less than 0, level curves of f of x, y, z is equal to z square minus x square minus y square are hyperboloids of one sheet. As an example, when k is equal to negative 5, the hyperboloid of one sheet is z square minus x square minus y square is equal to negative 5 and is shown in the figure. In this session, we discussed domain, range and graph of functions of more than one variable. We have seen that level curves and contour lines helps us to picture values of functions of two variables, while level surfaces are useful to picture values of functions of three variables. We expect that this session is useful to you. We will meet again. Have a great day.